Thank you, thank you. Hello, my name is Dave, and I'm a developer advocate with Google Cloud Platform. I'm super excited to be here in Portland, and I want to say a big thank you to the organizers for this awesome conference, and a thank you in advance to all of you for listening to me talk and laughing at all of my jokes. You're a great audience. Today we're going to talk about testing, and we're going to start with some motivations, some concepts, and then we're going to dig into a specific example around Kubernetes microservice applications. So this word continuous, we hear it a lot around here. Continuous integration, continuous delivery, continuous validation. Continuous is great, because when we move from discrete, batched, interrupt-driven kind of work and normalize it into continuous processes with small batch sizes, good things happen. First of all, we get those classic lean manufacturing benefits of less waste and more efficient use of resources. Secondly, by exercising our systems, we know they're going to work when we need them most, like in times of emergency. And thirdly, we treat our humans better. You know those 48-hour deployments that start Friday at midnight? It's kind of no fun. With continuous processes, we act almost as though the most critical things we do might actually be best if they're our day job. So the original continuous thing is continuous integration, and this came out of the nightmare of doing the merge. It used to be a bunch of engineers or teams would all work separately in their own little offices. For the young folks, an office is this room with walls. So they'd all be working separately and keeping their code separate and evolving it over days, weeks, months, and years sometimes. And when it was time to cut a release, they would all squish it together in one repo, and they would get conflicts. Because all of these streams had been separate for so long, and no one was really paying attention to whether they were going to work together. So they got smushed into one big thing, and there'd be tons of merge conflicts. Then the engineers would say days, maybe weeks, working through all of these conflicts, one by one, choosing which incoming change should win, trying to cobble together something coherent. And this made for bad times and bad software. So we invented CI, where we merge or integrate frequently, at least once a day. And we deal with conflicts when they're small and cuddly and manageable. Now, it's totally possible to do continuous integration and still have terrible software, right? We could resolve our merge conflicts by just randomly picking which one wins. It'd be really great for throughput. Not so great for software quality. So we added testing. And this means that today, in practice, continuous integration also means checking that code is okay to merge before we merge it. Or maybe slightly after it's merged. And I have feelings about that. We'll talk about that at a different time. So why test so often? Because yesterday morning, Gene Kim told us to. With reason. He said we need feedback loops that expose defects all throughout the process. We need feedback early and often and fast. And why is that? Because just like a Toyota, software gets more complex as it moves through the process. And that means the cost of addressing a problem grows as software progresses. A lot of folks here are probably familiar with the research that's been done by NIST and IBM talking about how a bug found in production costs way more to fix than a bug found in development. Different studies have found different numbers. Some of them said 6x, 30x. I even saw one that said 100x. Whatever the case, it's a lot of x's. And here's more data to support the value of testing. The DevOps Research and Assessment Group, or DORA, has consistently shown that continuous integration, or continuous testing as they call it, which I like, is essential to achieving continuous delivery. And having CD predicts both higher availability and more rapid software delivery. So you get faster and more reliable. And these capabilities have been shown to predict better business outcomes, like more profit. Speaking of the DORA Accelerate State of DevOps report, the new version was just released like 2 weeks ago, hot off the presses. It's a really good read. And if you stop by our Google sponsor booth, you can get a shiny piece of paper that has a QR code, scan, get the report for free. It's really great for understanding what high-performing teams are doing. It's got some ways to advocate within your organization. And if it's not something that you find compelling and interesting, tell us, because we're all totally sold on this idea. So tests are good. Now let's break this down. Here's what we call the test pyramid. We've got unit tests, integration tests, and end-to-end tests. There's some slop in these terms, but I'm going to define it like this. Unit tests are small and run quickly right alongside their code. Integration tests are when we put things together and make sure they can work together. And then end-to-end tests exercise a whole user journey across multiple steps. End-to-end tests are out of scope for today's conversation, but everything I'm going to talk about can translate upwards pretty much with no problem. In a microservice context, we're going to map this to unit tests run within one service or on one service. And integration tests are where we put multiple services together and test how they behave in conjunction. So this is an idealized test pyramid. And here's a real one. Usually we see a handful of unit tests, 0 integration tests, and this one brittle end-to-end test that is always broken, takes forever, and everyone just ignores it. No judgment here. Integration tests are hard. Why? First of all, whatever your production infrastructure is, you probably can't jam an entire copy of it onto your laptop. If you can, you either don't have a lot of users yet, or you have one hell of a laptop. Also, it can feel kind of wasteful to spend a lot of money on integration test infrastructure. No one's actually using that. Integration tests are often slow. The more stuff gets exercised as part of your test, the longer it's likely to take. And finally, side effects. The higher we go on the test pyramid, the harder it is to keep everything safely tucked out of the way. Most applications have state, and realistic tests usually involve manipulating that state, and then often manipulating it back. Microservices make it harder. Now, hooray for microservices. I'm not here to throw shade on microservices. We have reached the breaking point of monoliths. We need microservices. Microservices allow us to decompose an application and let each team independently build and deploy. It creates space between components, lets some air in so they can breathe. Microservice architectures deliberately separate streams of work and isolate each stream into something that a small team can take full ownership of. Small batches, more continuous, that's great. But I'm seeing a lot of microservices team doing something that kind of concerns me. They're building in isolation, and they're testing in isolation. It's like this. Each team tests their own service, and they might test the heck out of it, real good. And then they give it the stamp of approval, and they ship it. This means the first time the services meet each other is in prod. Doesn't this kind of remind you of those big, scary merges where everything goes wrong? The only difference is, in this case, it's not happening in some safe QA environment. It's often happening in user-facing systems where real people might be affected. So, okay, who cares? Integration testing is hard. Do we have to? Maybe. Let's look at the failure modes. Semantic versioning is a contract where every API advertises how much it changes with each release. This is good citizenship. Semver makes it so that each team broadcasts its intent clearly, so every other team can plan accordingly. But it's not always sufficient. Promises are meant to be broken. We can promise backwards compatibility, but until we test it, we don't really know if it's going to work. Emergent properties. When it comes to technology, sometimes 2 + 2 = OOM. No matter how well-behaved each of these little critters are, when they all hop into the pool, things are going to get weird. And most importantly, users don't give a hoot about your separation of concerns. If your front end touches 20 microservices and 19 of them are all playing nicely together, and one of them's kind of causing trouble, you don't have an application that's 95% working. You have an application that's 100% busted. So here's a hot topic, testing in prod. This idea comes out of the observability movement, and it says that we should treat our production deployments as though they are fundamentally uncertain and do quality testing after we've deployed them and remediate quickly when there's a problem. What do you think? Should we throw our stuff onto prod and then ask if it works? Yes. No matter how confident we are in our code, prod is different from not prod. Prod is where the users are, not prod is where they aren't. So things will break, and we should treat production deployments as uncertain and test them and respond. We should plan for failures and maybe even proactively trigger failures. Testing in prod is a really powerful way to think about how ops works, and And I think it's emerging best practice. But let's be clear about what this means. Testing in prod isn't some devil-may-care, haphazard way of doing ops. This is a disciplined framework for responding to errors, which are inevitable, instead of pretending that we can prevent all of them. But we can still pretend that we can prevent some of them. We don't have to give up on pre-prod testing. We should be thoughtful about it. It's about risk. We need to think about what could go wrong and what are the consequences when it does. So let's say you're running a site that makes meme GIFs. Meme, M-E-M-E, probably M-E-A-N as well. You're making memes. And one of the memes gets messed up, it looks wrong. What's going to happen? Well, the user's going to click retry. Or maybe they're even think it's cool that new version of the meme is weird and cool. Worst case, that person leaves and their internet points don't go up for that day. What if you're running an e-commerce site? I've had this experience of charging people money and not giving them things. That's less good. You've got a customer service problem, you may have a chargeback, probably other people in your organization are going to have to get involved. It's going to cost time and money to deal with that customer. So that's a business impacting problem. What if you're running the power grid for a hospital? We might want to be a little more careful about our deployments. We need to make informed choices about risk tolerance, and that these inform our approach to integration testing. Now, this presentation isn't about how to do a risk analysis. In my experience, it's typically been something really bad happened, our company barely managed to stay in business, and so next time we were like, oh, we should pay attention to that one. But if anyone has any ideas about a framework for risk analysis, I'd love to talk about it. Meanwhile, we're going to look at how to run integration tests when we decide that we need them. So one of the big complications with integration tests is provisioning. We need an environment to run our application in. Remember, that's environment, not microservice. We call this a system under test, or SUT. Now, there's lots of ways to do this with trade-offs between different dimensions, and we need to find an optimal balance. What are we balancing? The big six. Let's take a look at each of these. Fidelity. How similar is the test environment to prod? The closer it is, the more diagnostic the results will be, but also the more expensive and complicated the test environment is likely to cost. We can never achieve perfect fidelity in a pre-prod test because the users aren't there, but we can get pretty close if we decide to. Now, have you ever had this experience? You're running a test, a long-running test, and in the middle of the test, it all goes to hell. And so you shout across the office, hey, what's up with staging? And some guy's like, yeah, well, I dropped the database. I wanted to see how long it would take to restore. And you're like, well, how long does it take me to restore my test? Grr. We don't run these tests to interfere with each other. Ideally, when we start a test, we get a dedicated environment for that test that remains consistent throughout the test. It's also usually best not to test against external resources or APIs. Even if you're just doing reads, it's possible to DDoS your own systems or send some sort of malformed packet and totally break everything. Speed. According to Dora, reducing the time from commit to deploy is a positive and key DevOps metric. So we need fast tests so we can have fast deploys. Fast is better than slow. And once you get fast, what do you want? Always fast. No matter how fast our individual test runs are, at some point, if we've got more than one developer, we probably want to be able to run more than one test at a time. Because when my test is running slow and I'm waiting on it, I'm irritated. When my test is backed up behind some other jerk, I am infuriated. So for the health and safety of your organization, it's good to be able to run tests in parallel and scale these up. Ephemerality. Ideally, our test infrastructure lasts exactly as long as we need it. So that means it goes away at the end of the test, right? Maybe not quite. Yeah, I see. Because on a pass test, probably we're done, right? Good, it's green, move on. If it's failed, we might want to go in there and poke around and see what happened with that infrastructure. But at the same time, we don't want to leave it around forever and pay for it. So we need to find that balance of how long these things remain active. And cost, because, of course, no one wants to spend more money testing their application than they make from actually serving it to their users. And ideally, we control not only the total cost of doing our tests, but make it scalable with the usage so that we can always ramp it up or down depending on how our budget is. So we're going to look at an example. This is a microservices app which runs on Kubernetes, or K8s as we lovingly call it. And this is a cookie shop, an e-commerce site that sells cookies. It's made up of 2 microservices. But we all know that there are only 3 numbers, 0, 1, and infinity. So this microservice app has infinite microservices. Each one of these can run on its own and be tested on its own, but it's kind of boring. You can have a front end that doesn't have any inventory, no cookies. Or you can have a back end that you can talk to with SQL. Now, folks in this room might be thrilled about placing their Christmas cookie orders with SQL, but it's probably not going to get a ton of customers. So we want to put these together and make sure that everyone can get their cookies. Cookies for everyone, GDPR be damned. You can find the source code and some test configs for Google Cloud Build and Jenkins at that URL if you want to play along at home. Let's look at how we can test these things together as part of a CI pipeline. So I'm going to show 4 different ways to provision our infrastructure. They all test the same thing, but they use different techniques. The flow is the same for all of them. First, we build our containers for our different services. Then we provision them into a system under test. Then we run a simple test. In this case, it just curls and greps for the words a particular cookie item, chocolate chip, because that's the best cookie. And if it finds that, then it's going to deprovision the infrastructure. And if it doesn't find it, it may or may not, depending on the technique, be able to leave that infrastructure hanging around. So the first approach uses Docker Compose. Docker Compose is a lightweight way of combining container service, and it's great for developers because it uses a really simple configuration file to stitch containers together, and it runs anywhere Docker runs. All of the machinery in this case runs in a single VM environment, and that means that when the build's done, that whole environment's gone, no more paying for it. So this is fast and has 0 chance of orphaned resources. The downsides are that, A, you have to maintain a redundant configuration because unless you're using Docker Compose as your production infrastructure, which you probably aren't, it's going to be different, and that configuration can drift. There's no ability to go back to a failed environment and debug, so the fidelity is low. So that's ephemerality is low. The fidelity is poor because we're testing in different runtime than we're actually running against. So next, let's look at using an actual Kubernetes for the test. In this case, we have a Kubernetes cluster for staging. Of course, I'm using Google Kubernetes Engine. Each test creates its own namespace in Kubernetes, deploys the application to it, runs the tests, and then deprovisions that namespace at the end. If a test doesn't pass, that namespace is going to stay so we can debug against it. This method is fast, has high fidelity, especially if the staging cluster is run the same way as the prod cluster. Downside is it's not perfect isolation. The tests could stomp on each other. And you can't test anything that operates at the Kubernetes cluster level, like a custom resource definition, or if you want to test against different versions of Kubernetes. You can't do that with this option. Also, if a test fails, you can go in and debug it, but that infra is going to stay there and cruft up your testing infrastructure if you don't go in and clean those up. So what if we need perfect isolation and we want to control those orphaned resources? In that case, we can use a self-destructing VM. Wait, a what? All right. We're going to spin up a cloud VM instance to use as our test environment, and that's perfect isolation. But we could easily end up provisioning a ton of resources and leaving them idle after those failed test runs. If we don't manually go in and delete them, we're going to have them hanging around indefinitely. And the thing about an idle VM idle VM instance in the cloud is you're still paying for it, even if it's a zombie. So we're going to program this to delete itself. It's got a self-destruct fuse that activates after a preset time interval. How long? Well, that really depends on your purpose, on your own use case. Basically, the interval is how long before this infrastructure becomes irrelevant. Like, that's so old, it doesn't really matter to go in. I usually set mine for like 4 hours. To do this, we start this up with a startup script. And what that does is it sets a timer and schedules a job. And when that time is elapsed, say 4 hours later, the instance will make an API call. It makes an API call to the cloud API that says, I want you to delete instance 123. And 123 happens to be my name. Comes back, poof, and I'm gone. If you want to play with some self-destructing VMs, check out that link. So we're going to use that VM to run a lightweight version of Kubernetes on a single node. The demo repo has examples with both K8s and K3s. Hey, Rancher. There's also Minikube and a couple other things that do this. All of these are certified compliant Kubernetes runtimes that run on a single VM node. They're missing certain legacy features, and they don't really scale. But that means they start up fast and they're cheap, so they're great for CI. So now we've got a tiny little isolated Kubernetes environment to run our tests in. So now we have perfect isolation, and we can even do cluster-level testing. However, it's still not an actual Kubernetes cluster. So let's go all the way. For each test, create a dedicated, full-blown Kubernetes cluster, and then destroy it at the end of the test. Yes, this can be done, and I was surprised to find out that it's only a little bit slower than using one of these lightweight Kubernetes on a VMs. So now we have perfect fidelity and perfect isolation, and it's kind of expensive and kind of slow. So looking at all these together, you can see that each one has strengths and weaknesses. You might even find that you can make use of more than one. In an early stage, use kind of one of these lightweight, lower fidelity options, and as you progress, maybe spin up a whole cluster per test. But there's really no best option, except there kind of is. In my opinion, in most cases, I think that having every test deploy to a separate namespace on a shared staging cluster is best. And this is extra good if your cluster is configured to auto-scale up and down, so you're only going to pay for the resources you're using. Now, my instinct is to recoil in horror from saying everyone should use a single piece of infrastructure. Remember the shouting across the office? But Kubernetes namespaces have really pretty good isolation. A process in one namespace is not going to reach out and connect to another namespace unless you deliberately tell it to. Yeah, you're going to have some orphan namespaces, but honestly, that's not that expensive or compute intensive. A bunch of old namespaces hanging around are not that big of a deal. And you could always create a script to clean them up every once in a while. So there are lots of good ways to run integration tests for microservices. But Dave, what if you have lots of services, dozens, hundreds? It could take a long time to run all of those tests. Yes, it could. So we might need to find a balance. We might need to use some stubs or mocks. Or it may be that we have some static, standing, long-running instances of some services, like the ones that don't change very often. There, we don't really feel like we need to instantiate them every single time in every test. But Dave, what about stateful storage? I'm not running my database inside my Kubernetes, right? She's not, there was a shout out right there, right? Yeah, thank you. In the example I showed, we spun up a test database as an ephemeral service. And so that's a reasonable kind of facsimile. But you're going to get deeper stuff if you have a proper database that's probably outside the cluster. If you're using database as a service, you can do something where every time you spin up a database on that service and deprovision it using the database API. Across the board, a challenge here is database size. Your production database could easily have terabytes or petabytes of user data. And provisioning one of those for every test is going to be super, super painful. Testing against a smaller data set, however, doesn't reveal all the challenges like slow queries or hard drives filling up. So it might make sense for some cases to have that persistent staging database that everything can run against, or some things run against at certain times. Speaking of user data, but Dave, what about PII, sensitive user data? This one's tough. To get highest fidelity tests, you were going to run against actual prod data. No, that's probably a no-no in most situations. So we're going to run against test data that kind of tries to look like the same shape as your prod data. It is possible to have something where you export your prod data, sanitize it, import it into test. You can even do that on a schedule every week and have always fresh data. That's really pretty cool, but it's a lot to maintain, and it might not be worth it. And that's really the question I hope we're asking. Not, can I be excused from integration tests? But is it worth it? I know it's possible. I've thought about the risks and the costs. What's my sweet spot? To sum up, we have choices. We can choose to take a whole bunch of time and effort and completely test the living bejesus out of every release, every commit before we deploy it. Or We can fire it into space on a wing and a prayer, deploy it all and let the users sort it out. The right answer is probably somewhere in between, and it's going to be different for every situation. I would love to hear about your situation, so please come chat with me or tweet at me. Tell me what's working for you. Thank you.